Hello and welcome to another session in physics. In this session we'll be looking at the topic models of the atom. But before that, let us review the previous lesson. Welcome back. We'll start by looking at Thomson's model of the atom. Remember, in previous lessons we've already defined an atom as the smallest indivisible particle of an element that can have a separate existence and still have the characteristics of the element through which it came from. Now, Thomson proposed an atomic model which visualized the atom as a homogeneous sphere of positive charges, inside of which we find embedded negatively charged electrons. He also discovered that the ratio of charges to mass, in other words electron charge over mass of electron, was found to be identical for all cathode ray particles, irrespective of the kind of gas that was in the tube or irrespective of the metals that the electrons were made of. As you can see from the diagrammatical representation here, you would notice that electrons are depicted to be part of a spherical cloud of positive charges, with the electrons existing very close to the outer shell. But Thomson's atomic model had some limitations. The first is that Thomson's atomic model failed to explain how the positive charge holds on to the electrons inside the atom. In other words, it failed to explain how an atom is stable. Also, Thomson's atomic model did not mention anything about the nucleus of an atom, and we know full well that an atom is nothing without the nucleus. And finally, Thomson's atomic model was unable to explain the scattering experiment of Rutherford. Now let's look at Rutherford's model. Rutherford proposed a planetary model for the atom which suggested that the atom consisted of positively charged heavy core, which we call the nucleus. It is at this nucleus that most of the mass of the atom was concentrated. Think of it more as the center of gravity of the atom. Around this nucleus, negatively charged electrons move in circles, in orbits, the same way that planets move round the sun. Each nucleus must be surrounded by a number of electrons, which is necessary in order to produce an electrically neutral atom. So for us to bring about electrical neutrality, the number of electrons must be equal to the number of protons. When the number of electrons is equal to the number of protons in an atom, we say that that particular atom is electrically neutral. Same as Thomson's model, Rutherford's model also had some limitations, about two of them. The first limitation of Rutherford's model is that it predicted that light of a continuous range of frequency will be emitted. But on the other hand, experiments showed that this was wrong because Rutherford was propagating the line spectra, where experiments showed continuous spectra. The second limitation of Rutherford's model was that it predicted that atoms are unstable electrons and that they quickly spiral into the nucleus. But in general, we know that atoms are stable, since the matter around us is stable. So clearly, Rutherford's model was not sufficient enough to explain experimental observations. Do remember that in science, it is not just enough to have a hypothesis or guess. As much as we have a hypothesis or guess, we also want to prove that hypothesis by carrying out an experiment. After this experiment, we'll be able to arrive at conclusions that will help us to know whether the hypothesis initially was correct or not. So some sort of modification was needed on Rutherford's model, and this modification was provided by Niels Bohr. Now, Niels Bohr's model suggested a model of hydrogen atom in which the electron moves around the nucleus in certain specific circular orbits we call energy levels. Certain specific circular orbits we call energy levels. Now, these energy levels are as a result of a centrifugal force which balances the electrostatic attraction between the electron and the nucleus. Notice that electrons can move without losing or radiating energy when they move in such orbits. This is what Bohr called possible stationary states. The state at which electrons can move without losing or radiating energy is called possible orbit stationary state. And this was only possible in orbits of a particular radii. So in general, Bohr was trying to say that the higher the energy of the electron, the farther it moves away from the nucleus in its orbit. Secondly, Bohr's model was postulating that the energy of an electron in an atom cannot vary continuously to a limited number of discrete or individual values. So at that point, we say that the energy of the electron is quantized. When we say quantized, we mean that the energy has only discrete values. In other words, it can carry out what we call quantum jumps. It can move from a lower state of energy to a higher state of energy, and similarly, it can also move from a higher state of energy to a lower state of energy. And when such a quantum jump occurs, a single photon of light would be emitted, whose energy is given by this equation you see right here on the screen, where we have EU minus E1, EU being the energy of the upper state or upper level energy, E1 is the energy of the lower state or lower state energy, and then we have H, which of course refers to Planck's constant with a value of 6.67 times 10 raised to power minus 34 joule second. And then our frequency is the frequency of the emitted light. When we're talking about radioactivity in previous lessons, we said that when electromagnetic radiation is focused on metal plates, it causes photons to be emitted. These photons that are emitted is what we refer to as energy quantization. Fortunately enough, Bohr was able to account for the appearance of line spectrum rather than continuous spectrum. He provided proof for that, unlike Rutherford. The third postulate of Bohr's model was that angular momentum values of the electron in an atom are quantized. In other words, they are restricted to a limited number of discrete values. Remember once again that when we say something is quantized, it means it is limited to a discrete number of values. Now, these values are called integrals. They are multiples of a constant, which is Planck's constant, divided by 2 pi. Dividing by 2 pi means it's going to give us an angular momentum, since it moves at an angle. N, on the other hand, is the integral number or quantum number, which represents energy levels, where we have energy level 1, energy level 2, level 3, and level 4, respectively. Bohr's model is also known as the Bohr-Rutherford model, because basically what Niels Bohr was doing was an extension of Rutherford's planetary model, only that he was able to provide proof for the line spectrum that Rutherford was unable to do. Now, Bohr's model was very successful out of both he and Thomson's and Rutherford's model. There are about 4 reasons why his theory was a great success. The first reason is that his model gave a reason why atoms emit line spectra, and he accurately predicted for hydrogen the wavelengths of emitted lights or the frequencies of the lines in hydrogen spectrum. The second reason why his theory was a success was that he offered a very plausible explanation for absorption spectra, where he said that photons of the right wavelength can knock an electron from one energy level to a higher energy level, and that for photons to conserve energy, that photon must have exactly the right form of energy. And this helps to explain why a continuous spectrum passing through a gas will have dark absorption lines at the same frequencies as the emission line. The third reason why his theory was a great success was that it ensured the stability of atoms by stating that the ground state is the lowest state for an electron, where an electron would not be able to go beyond, and that there is no lower energy level after the ground state to which an electron would be able to go and emit more energy. And then the fourth reason why his theory was a great success was that it was able to accurately predict the ionization energy of 13.6 electron volts for hydrogen. Now let's talk about the electron cloud model. The electron cloud model seems to visualize electrons as existing inside a cloud and spending most of its time in certain high probability regions, with all of them being in rapid motion around the nucleus. Thus, the electron is not considered as a ball revolving around the nucleus, but it is considered as a particle or wave, more like a cloud with a specified energy having a certain amount of probability of being in a given region in the space outside the nucleus. So they look at it more as a sort of spread out around the nucleus in some sort of what we call electron cloud, with the cloud, according to chemists, being dense or thicker in regions of high electron presence and more diffuse or scarce in regions of low probability. At this point, let's talk about the atomic structure and chemical behavior of atoms. Today we consider the atom to be made up of tiny but massive nucleus at the center, and outside the nucleus we look at it as having a cloud of electrons which hover and move in wave-like orbits or shells around the massive nucleus. Now it's important to note that this nucleus consists of protons which carry positive charges and neutrons which carry no charge at all. The neutrons and the protons together constitute the nucleon. The electrons are not part of the nucleon because they exist at the outer shell of the atom. So the protons, neutrons and electrons are all the fundamental subatomic particles of the atom. Now when we talk about isotopes, we are referring to atoms of the same element which have the same atomic number X, but they have a different mass number. Isotopes have the same atomic number, but they have different mass number. So isotopes are thus atoms with the same number of protons, but they have different number of neutrons. Isotopes have similar chemical properties because they have the same number of electrons round the nucleus. So chemical combinations are due to an exchange of the outer or valence electrons that exist between elements. So always remember, because in your WAEC you will encounter questions on isotopes, remember that they have the same atomic number but they have different mass numbers. We'll consolidate on this in next lessons. Thank you for joining us in this lesson, and to refresh your memory on what we've just discussed, please take the test that will appear on your screen.